Hello, my name is Walter Unglaub, and this is the type of diffusion applying only to ions. So there are many different types of ions and ionic systems and scenarios, and the types of ions that I'm going to be considering here are ions that can penetrate, for example, through cell membranes. So if I have an either positively or negatively charged particle, for certain types of membranes, there can be a flux of ions passing through this membrane. And diffusion is essentially a way of describing how this flux depends on the properties of the ions and the environment and the membrane as well. So there is a diffusion equation where I have a diffusion constant equal to mu kBt, where T is temperature, Kb is the Boltzmann constant that one can think of as a conversion factor between temperature and energy, and mu is what's called the mobility of the ions. So this mobility can be thought of as a diffusion velocity divided a force. And the units here for velocity are in meters per second, and the units of force are newtons, and 1 newton is equal to 1 kilogram times a meter over second squared. So if I'm dividing by force, I have kilogram times meter over second squared. The meters cancel out, so I'm left with seconds over kilograms. And then the units of kBt, this is a type of energy. So as you increase the temperature, these ions, these particles will be moving faster. And the units of energy is joules, which is equal to Newton times meter, which is equal to kilograms times meters squared, because of this extra meter, divided seconds squared. And when I multiply this unit with the units of mobility, so I bring this down here, I can see that the units of mass will cancel, the kilograms, and the unit of seconds up here cancels with one of these, so I'm left with meters squared per second. So that's the units for diffusion, for the diffusion constant. And what it represents is the greater the diffusion constant, the greater the area that a number of ions will pass through in some unit of time. So you can think of this as an inverse time scale, for example. And this parameterizes the rate of diffusion then of these ions through a membrane. There are many other types of ions, such as the ones encountered in plasmas, and those diffusive properties are certainly also very interesting, but also very complex, because the magnetic fields associated with controlling the plasmas, meaning the collection of ions, can introduce many nonlinearities in the dynamics. And generally, the diffusion for these types of ions will be inversely proportional in some sense to the magnetic field. So the stronger the magnetic field, the tighter the orbits of these charged particles, these ions, about the magnetic field lines, and hence the diffusive processes will diminish. My name is Walter Unglaub, and this is the type of diffusion applying only to ions.